In this video we are going to compute the length of several curves. In addition, we introduce the notion of the arc length parameter, a very useful tool to get theoretical results for curves. We start by giving the definition of the length of a curve. For a differentiable parametrized curve alpha, defined from an interval I into R2 or R3, and given 2 points of the trace, point P equals alpha of C and point Q equals alpha of D, the length of the arc of the curve between the values C and D measures the length of the piece of the trace of the curve, drawn in blue color in the picture, as if we were stretching the curve. In order to calculate it, we have to compute the integral between C and D of the norm of the derivative of alpha, that is, the formula at the bottom of the screen. To give an idea of the proof, we approximate the curve by a polygonal path, each segment connecting 2 points of the trace of the curve. Then, our first approximation of the length of the curve is going to be the sum of the lengths of the segments. But we can get a better approximation of the exact length by taking a larger number of segments, or even larger. In the limit, the sum of all the lengths is the integral, and the segments measure the modulus of the derivative, that is, the speed of the parametrization. If we have an open interval I given by A and B as the initial and final points, we can calculate the length as the limit when C goes to A and D goes to B of the integral between C and D of the norm of the derivative of alpha. Note that this limit may not exist. And as we will see later, the length of a curve is independent of the parametrization used to compute it. This is true because, in fact, a change of parameter is equivalent to a change of variable in the integral, and this does not change its value. We start by calculating the length of the arc of the circle, with center 0, 0 and radius r, between the values t0 and t1. We already know that the parametrization of the circle can be given in terms of the sinus and the cosinus. And it's easy to compute the derivative, and we check that the norm of the velocity equals the radius r. Hence, the length is the integral between t0 and t1 of the constant r, and therefore equals r times t1 minus t0. When t0 equals 0 and t1 equals pi, then we have that the length of the semicircle is pi times r. As we mentioned before, the length of a curve is independent of the parametrization we use for its trace. To illustrate it, we calculate the length of the upper semicircle with center 0, 0 and radius r with the following other parametrization. We recall here that all the points of the upper semicircle satisfy that y equals the square root of r squared minus x squared. Now, we just rewrite x as t and t between minus r and r. After some easy computations, we get that the modulus of the derivative of alpha satisfies the identity you have now on the screen. So after calculating the integral, we get that, also using this parametrization, the length equals pi times r. Another example, now with a space curve, is the length of one arc of the helix. We have seen in previous videos the parametrization. This parametrization is written in terms of the radius r and the pitch per twist a. Now we compute the derivative and the norm of the derivative. This norm is constant and takes the value of the square root of r squared plus a squared. This constant times 2 pi is the integral between 0 and 2 pi and gives the length of a complete turn of the helix. Another example. We can compute the length of the best supporting arc that we have mentioned in a previous video. That arc, we will see in a subsequent video, has the shape of a parabola and can be parametrized as follows. We compute the derivative and the norm of the derivative. The integral can be calculated after a change of variable. The value of this integral would be essential, for example, to calculate the quantity of iron necessary to build that arc. Another interesting example is the calculation of the length of one branch of the roof of the building Tempelbau in Berlin. A possible parameterization for each of them is the one that you have now on the screen. We compute the derivative and the norm of the derivative, but now, in this case, we need numerical techniques to compute the integral, since we cannot find the primitive function to compute that length. This fact happens very often. The goal of the rest of the video is to introduce a new parameter, called the arc length parameter. This is very useful to prove very important results for curves. We define the arc length function s of t from a point alpha of a as the integral between a and t of the norm of the derivative of alpha. S of t is the length of the piece of the curve between alpha of a and alpha of t. And we are going to see that this function can be used as a parameter. We start with the example of the circle of centers 0, 0 and radius r from the point r0, that is when t equals 0. We have already seen in this video the parameterization as well as the derivative and the norm of the derivative. It's easy to see that the function s of t equals r times t. Then we have a relationship between t and s, and we can rewrite the parameter t in terms of s, and therefore we can also rewrite the parameterization alpha in terms of s. In fact, what we have done is the inverse of the function s, which geometrically can be found by reflecting the original graph across the line s equals t. This is equivalent to switching the axes. This can be done for any regular curve due to the inverse function theorem. This theorem guarantees that every regular curve admits a parameterization by the arc length parameter. This parameterization is also called the natural parameterization. Sometimes it's not easy, even if alpha of t is regular, to express t of s in terms of elementary functions. For instance, this is the case of the parabola that we have seen previously, when we use the parameter arc length starting from 0. We know the expression of s of t. This, in fact, describes t of s implicitly and allows us to draw it. But we cannot find an explicit expression of t in terms of s as a combination of elementary functions. We now show another example, in this case the helix of radius 2 and pitch per twist the square root of 5. We calculate its derivative and the norm of the derivative. This norm equals 3. Then s of t is 3 times t, and t of s is s over 3. We can rewrite the helix by the natural parameterization as it appears at the bottom of the screen. When the helix is parameterized by t, the speed, that is, the norm of the derivative, equals 3. This is the green vector on the image. But when the helix is parameterized by s, then the speed, the norm of the derivative, equals 1. This is the pink arrow of the image. This fact, that is, the norm of the derivative being 1, is always true in the case of the arc length parameter. Then, the length of any piece of the curve, when the parameter moves s units, equals s, since the speed is 1. In other words, when the curve is parameterized by the arc length, the speed equals 1 for every value of the parameter s. For example, with the ellipse, the norm of the derivative, the pink vector, changes from point to point with the parameterization we introduced in previous videos. This parameterization is not the arc length parameter. The arc length parameterization would have given a vector, the green vector, of constant norm. With this arc parameterization, the arc length function equals s minus c, that is, the length of the segment cs. Summarizing, the arc length parameterization, or sometimes called the natural parameterization, always exists. It comes naturally from the shape of the curve, its trace, and does not depend on a particular coordinate system. When we parameterize a curve with respect to the arc length parameter, the speed, that is, the norm of the derivative, is constantly 1. And the arc length parameter allows us to obtain theoretical results that can be generalized for any other parameterizations.